So hello everyone. Today I'm Jessia, not Katrina Exter, and I'll be talking about the work I do with the haircuts data. So I'm really glad that Toshia already set the stage for me, so all I have to do now is to show the pretty images. What I'll be showing is only the photometry data part of the hair plans data, so I really hope you still have in mind all the details that Toshia gave about the observations, because I'm not going to go over that again. Okay, so far, what we saw about planetary nebulae, it was mainly like gas, jets, more gas, hot bubbles, more jets, binary interactions, and jets again. So this is a bit of a change of scenery, because what I'm interested by is where is the dust in planetary nebula. And so what we are tracing with the hairplans data is the outer, very extended halo. And so far we saw only one image of that was shown by Shahrazad yesterday. And this is NGC 6543, and we see this very nice extended halo that is seen in the narrowband optical images. So this halo, we see it ionized, fully ionized or partially ionized depending on the excitation state. And so it's believed to be a remnant of the AGB star phase. And so if it's a remnant of the AGB star phase, would we see the dust? So there are Spitzer data that actually resolve those extended halos as well. And Spitzer spectroscopy data do show us warm dust in them. And so what I'll show you is where is the cold dust. Okay, so I'll be showing hairplans photometry data and compare them to optical and mid-infrared data as well. So I'll start with NGC 40. So NGC 40 is a low excitation planetary nebula electrical. So on the left we have the H-alpha map, and on the right you have the hairplan 70 micron map. On the top right you have the beam size for our data. And so in the H-alpha we see the very bright elliptical inner core, and we basically resolve that as well at the 70 micron map. And so if we zoom out, here we have a multi-wavelength panel of images. So in the H-alpha, I tuned the intensity cuts to enhance any faint emission. So you see a jet-like structure in the north east direction. And so in the mid-infrared with Spitzer data at 8 micron, we see this very nice extended halo. And that extended halo is also resolved at longer wavelength with hairplans data at 70 up to 500 micron. Although at much longer wavelength, we have some background sources that start showing up and polluting the image. So this halo is fairly spherical. Another example is NGC 7009. So this one is a high excitation nebula, elliptical as well. And so what we see in the H-alpha image is this very bright inner core with like a bright ring, and around it, and then we have also an outer shell, and you see some streams, and we have unsafe. And so at 70 micron, we just resolve the bright inner core, and we see the outer shell as well. And we don't, with our resolution, we can't resolve the streams or the unsafe, but we can see where they are located based on the way the elongation of the structure is. Again, when we zoom out, so this object in H-alpha and O3 shows a very extended, very patchy outer halo. It's much brighter in O3. Well, the structure is blacked out because of saturation, to avoid saturation. So it's interesting to note that at 8 micron in Spitzer data, we don't actually see this extended halo, and this is not present in the 4 channels of Spitzer. Well, we pick it up again in the far infrared, so we have this extended halo here that we see at longer wavelengths. So usually, out of our 11 targets, we see those extended halos in 9 out of 11, like clearly. And usually, if we see that in narrow bands, and we see that also in mid-infrared and also in the far infrared, except for 2 objects in our sample, and that's NGC 7009 and also NGC 7026. So for this one, I don't have any narrowband images data, but we also see here that there is no extended outer halo in the Spitzer data, but we see one at 70 micron, and then it's still present at longer wavelength, although there is also some background contamination that shows up at longer wavelength, and it picks up as we go higher and longer in the wavelength range. So what's happening on here? So why don't we show those halos in the mid-infrared, we see them in the far infrared and the optical? So that can be linked basically to chemistry, because the 8 micron band in Spitzer is believed to be dominated by pHs light. So basically, this can be an indication that we don't have any pHs for those objects. So the question is, the light we see in the far infrared, where does it come from? Is it really from the dust or from something else? So this just shows you a packed spectrum. We don't care what object it is. I have overplotted the transmission curves from the photometers at 70 micron and 160 micron, and I highlighted only the lines that are susceptible to contaminate our emission line in the broadband maps. And so basically, if you have a very strong continuum, if you have a good detection of the continuum, the dominant light will come from the dust emission with some contamination from the lines. But if your continuum is very low, the contamination from the lines will become. And well, same for like both wavelengths. And because we have spectroscopy data combined with our photometry maps, we can make estimates of how much of the line contamination we have in those data. So what can we do with those data? So we can do aperture photometry on the data. So to do so, we choose an aperture that's based on the 3-segment detection on our 70 micron maps. So that's the contour from the 70 micron map was used as an aperture for all the maps because that's our best detection. And we took the 5 total fluxes and we fitted them with a modified black body to derive a dust temperature and also a beta and a dust emissivity index. And so this, you don't have to try to read the fitting parameters. All you need to see here is the quality of the fit. What I wanted to show is that we have a fairly good fit. It's very well constrained. The error bars are very small, although here we have both error bars coming from the fitting and also from the flux calibration of the instrument. There are 2 fits here. So there is the black dashed line, and that's fitting just the total flux. The red line is actually the fit when we subtract what we believe is the contribution from the lines. And so what happens when we do that is that if we don't consider any line contamination, the average dust temperature in the nebula we find is in between 40 to 90 K. But if we take into account line contamination, for some objects, the dust temperature is still low, but for some of them, the average dust temperature picks up and becomes higher. So how well is this representative to the distribution of the dust if we're looking at them as spatially resolved objects? So because we have 5 photometry bands, what we could do is basically fit the temperature for each pixel through the 5 maps and get resolved dust temperature maps. So my first example is going to be NGC6826. Again, it shows a very nice extended halo in our bands and also in the far infrared, fairly spherical again. So when we fit the dust temperature for this, so the average dust temperature tells us that we have a dust temperature around 140 K. But actually, when we look at the spatially resolved temperature map, which is here on the left, what we see those very white patches. So those correspond to very high temperatures. It's basically dust that's high with the temperature that's higher than 250. All we know is it's higher than 250 because we cannot constrain it as it peaks at much shorter wavelengths. But we know it's there and we know it's much warmer. So the average temperature doesn't reflect that because it just averages the temperatures across the whole nebula. But if we look at the spatially resolved distribution, we can see that we have a very warm dust component and we have colder dust around it as well. And so just to make clear, everything that's blacked out in the maps is basically bad fits. So I already trimmed the bad fits out and everything that I'm showing here is actually good fits, what works well. And so we have also the beta map in the middle, but I don't think I have time to that should reflect the chemistry we have. And if you're interested by that, you can discuss that with me later. And we see the overlay of the temperature over the beta map and also the age of emission. Another case, NGC 2392. So this one, we don't see an extended outer halo. This object is also in the Romano-Corradi survey, and they also don't find an outer halo in the narrowband images. And so it doesn't show much also in the far infrared. And so if I do the temperature fit for this, so the average temperature fit shows here that I have a 50K dust temperature. But if we look at the resolved temperature maps, we see that we have colder dust with like warmish peak in the middle, but we have again this warm dust component that just around the cold dust components. That's a different type of dust distribution temperature that we see in our data, and that happens for 2 objects out of our 11 objects. To be fair, they're not all of them like that. So for NGC 1726, for which we don't have an outer halo in the mid-infrared, but only in the far infrared. So for this one, if we do the spatially resolved dust temperature maps, it's cold dust of around 75K. And in this case, the average temperature corresponds to what we see in the dust temperature map, the spatially resolved dust temperature map. So for some of the objects, it actually does work. So what is next, basically, for us? This is entering the construction zone. So careful, anything might fall on you. And so, in the very near future, what Toshia showed some of this is that what I'm working on right now is trying to derive dust masses, because you need to remember that what we saw up to now is dust temperature distribution, so that doesn't trace the density. And so what we can do, though, is derive column density maps and derive dust masses. But this is very dependent on the chemistry, which I'm still trying to disentangle using between spectroscopy and the photometry data I have. And so for now, what I can tell you, though, is that the dust masses I find in those nebulae are in between 1 to 10 to the minus 5 solar masses to 3 to the minus 3 solar masses. That's quite a bit. This is a very conservative estimate, actually, and it's quite a bit of dust that we see out there. More in time, this is more of a danger zone. So Toshia already mentioned that as well. So what we hope to do is to be able to do a very detailed analysis like the one that he showed for 6781 for all our targets, but also make a very detailed version of transfer codes. But that's very challenging in light of how complex our data set is. I mean, the complexity of the models is like directly correlated with the resolution you have, the sensitivity, and how big of a data set you have in like wavelength range coverage. But hopefully that's what we aim to do for the future. So I'll leave you now with all the images from hell planets at 70 microns so they can see all the outer halos that we detect. And thank you very much.
So we have time for a few questions.
For the Saturn nebula NGC 7009, this hexagonal morphology, is it real or does it have some kind of
so far I think it's real, actually. It's also very similar to what we see in 65 or 23. It's like sort of hexagonal.
Okay, thank you.
Anybody else? There's one, right?
I was just wondering about the environments. Do you know where they are? Because the one that you have the really high temperature at the edges, that I guess to be rich from the ice, right? But the environment of them, is it very isolated or?
Well, it's not quite clear for those, but for the 2 objects we see that they don't have much of any extended emission in the infrared, not really mid infrared or far infrared actually. And so it can be that they are in a very ionized part of the sky. So it can be also depending on the airs that they have around them. But I still haven't investigated that. So it's a possibility.
Joe?
Microphone is here. So other than the ones in which CO had previously detected 6720, the ring, and 6781, and is there CO in any other nebula?
Oh, yeah. So
Yes.
so we see like the 6445, 6781, and what was the other one? I think 68.
I guess my question
But
is...
not in, we see that only in 3. Actually, yeah, that's why when I was talking about line contamination, I just showed the packed spectrum and not spire, because we're concerned about that only at 70 and 160 micron. Because for most of them, we don't see any emission lines in the spire wavelengths. So line contamination is not an issue there.
So any CO that may have been there primordially, that is from the AGB phase, has long since dissociated.
Yeah.
Thanks.
Okay, we will move on to the next talk, and this is Ivan Nature versus Nurture, the influence of environment and the formation of the solutions.